Let's jump right into this explainer. Today, we're cracking open the Insider Playbook Equilibrium of Forces and Vector Triangles. And right off the bat, the source material hits us with a pretty harsh warning. If you're taking shortcuts on vector triangles or the principle of moments in your Physics 9702 exam, you are literally throwing away easy method marks. So let's figure out why so many candidates fall into this exact trap and how we can use this playbook to completely secure those grades.
It's honestly fascinating to look at the core problem highlighted here. Why do students find it so incredibly hard to apply equilibrium concepts to unfamiliar contexts? Well, the sources point to one major culprit. Candidates are trying to memorize generic textbook answers instead of actually mastering the analytical process. And, walking into an exam with a rigid, memorized script, it just doesn't work when the test throws a scenario at you that you've never seen before. If you don't really get the underlying principles, all that memorization just falls apart the second the physical setup changes.
And the stakes here are absolutely massive. We know this because it's spelled out directly in the principal examiner reports. They explicitly state, most students lose easy marks on equilibrium of forces. Answers are not specific to the context given. I mean, that is undeniable proof right from the source that ordinary rote revision just totally fails here. If you just jot down a formula without actually tying it to the specific beams, the pivots, or the exact forces described in the scenario, you can kiss full credit goodbye. The physics has to be grounded in the reality of the question. Okay, so before we get into the more advanced strategies in the playbook, we really have to make sure our theoretical foundations are rock solid. Let's lock in the precise definition for the principle of moments. For a body in equilibrium, the sum of clockwise moments about a point equals the sum of anti-clockwise moments. Sounds pretty simple, right? But the absolute secret weapon revealed in the text is buried in that one little phrase, about a point. It's not just about forces magically balancing out in space. It's all about that rotational turning effect anchored around one specific, consciously chosen pivot. Honestly, missing that tiny detail is exactly where so many points just get left on the table. Building on that idea, the playbook gives us the exact conceptual framework for general equilibrium conditions. For an object to be in true equilibrium, two very distinct conditions have to be met. The net force must be zero, and the net moment must be zero. If you're dealing with three coplanar forces, visually this perfectly translates to a closed vector triangle. Just imagine those three arrows meeting up perfectly, tip to tail, forming a complete closed loop. If there's even a slight gap and they don't connect, that object is accelerating. It's definitely not in equilibrium. This closed loop is the exact visual proof the playbook tells us to draw to really secure our footing in these questions.
And this really highlights a huge academic benchmark. The materials show us that Cambridge examiners heavily prioritize deep, structured reasoning way over a superficial breadth of random formulas. Superficial breadth is basically when you panic and just write down every physics equation you can think of, crossing your fingers that one of them gets you a mark. Analytical depth, though, that means taking one single solid principle, like that closed vector triangle we just talked about, and logically following it all the way through the specific scenario on the paper. It's about showing you can actually think like a physicist rather than just acting like a photocopier.
So to actually survive these really complex questions, the text outlines an unbreakable procedural framework. It's not a random scramble, it's a very specific sequence. First up, you identify the key elements, like your pivots and forces. Then apply the relevant principles, like balancing those moments. Once your setup is crystal clear, you execute with really clear working, verify that your results actually make logical sense, and finally present it all in the correct format with the right units. It creates the standardized rhythm. And let me tell you, skipping a step in this logical flow is a guaranteed way to skip a mark. Now, the playbook mentions a highly specific examiner clue that completely changes how you calculate moments. We'll get to that in a bit, but according to the text, you honestly can't even spot that clue without having this analytical framework firmly in place first. If you just rush ahead and skip the framework, the clue stays totally invisible, which leads you straight into calculating the wrong perpendicular distance. So holding on to that procedural rhythm is absolutely crucial before you go hunting for any hidden clues. To actually spot those clues in practice, the material pushes this deconstruct, solve, and evaluate rhythm. Start by deconstructing the problem, extract the data, and draw a free body diagram to turn all that chaos into pure logic. Next, solve it systematically, step by step. And finally, this is critical, evaluate.
check for reasonableness. If you calculate that the force holding up a simple little wooden shelf is 10 million newtons, your evaluation step should immediately be screaming at you that something went incredibly wrong. That built-in reality check is an absolute lifesaver.
Let's look at a direct comparison of approaches. The flawed answer completely skips the vector triangle setup. It gives zero context and just kind of scatters random numbers onto the page, making it totally impossible to figure out what pivot point is even being used. But in stark contrast, the top band examiner answer executes with just beautiful clarity. It clearly specifies the pivot, uses exact notation and precise terminology, and follows the perfect format. The logic flows so well that honestly, even if a tiny calculator error slipped into the final number, the brilliant thought process is completely undeniable.
And that brings us to a pretty shocking reality: 0. 0 is exactly how many marks you're going to get if you adopt that flawed strategy and just refuse to show you're working. Why? Because the method mark strategy highlighted in the guide is literally everything. Method marks can save your grade even if your final answer is totally wrong because of some silly math error. A naked, incorrect final answer leaves the examiner absolutely nothing to grade. But clear, methodical steps, that might secure you 3 out of 4 marks on a question where the final number is completely off. It's a huge realization.
Now, when we get into evaluating evidence quality, especially in the practical or data analysis sections, the data strongly suggests rigorously mapping any limitations directly to their effect on your final conclusion. Vaguely saying human error is just not going to cut it. The guide absolutely insists on stating the specific limitation, like, say, the assumption that a beam is perfectly uniform, and then explaining exactly how that one specific assumption impacts the final calculated tension in your vector triangle. Mentally mapping these elements to their precise effects is how you really build strong critical analysis.
Interestingly enough, if we look at the most common red flags directly from the principal examiner reports, it shows us exactly where students are hemorrhaging marks the most. The number 1 mistake? Failing to include proper format. Number 2 is poor presentation, when the working out becomes this chaotic mess that literally no one can follow. And the third major pitfall is a lack of specific context. Think back to that earlier advice. If a scenario gives you a crane lifting a steel beam, and your answer just talks generally about a rod, that perfectly demonstrates that lack of specific context they're docking points for.
So how exactly does the playbook suggest we stop losing these easy marks? By using a visual story method to deeply encode these concepts into our memory. Instead of just rote memorizing a phrase like net force is 0, visualize it. Picture 3 arrows forming a closed loop, walking perfectly back to the exact spot they started. Picture a seesaw that is completely balanced, with the turning forces neutralizing each other in real time. Encoding the physics as a logical, visual story completely removes the need to rely on shaky, panic-induced memorization when you're under the stress of a ticking clock in the exam hall.
So we've explored the framework, the core definitions, and the major pitfalls from the text. But this leaves us with a pretty dangerous, unresolved problem. What happens when they throw a massive curveball? What are you supposed to do when the exam forces you to apply these equilibrium rules to a completely bizarre, unfamiliar practical investigation design that has never, ever appeared in any past paper? That right there is the ultimate test of analytical depth, and mastering how to navigate that unknown is absolutely essential for top marks.
To navigate those insanely complex, unfamiliar scenarios outlined in the source, you need to find that safe shortcut. Bridging to our next explainer on common traps by question type is definitely your mandatory next step. You can catch more of these deep dives by subscribing to Ace the Exams on YouTube. But unpacking this playbook leaves us with one final, pretty provocative question to ponder today. If true mastery in physics is really about adapting your reasoning to the completely unknown, are you currently studying to actually understand the physical universe, or are you just studying to memorize a textbook?